This is going to be a video investigating the following problem. Enumerate all 1-octave scales of n tones with no more than m consecutive tones using a 12-tone system. This became interesting to me when I heard Alan Holdsworth talk about his method of organizing pitch or trying to approach harmony in a way. I guess what he was looking for was maximum freedom and to go to different sounds and explore as much as possible. He describes in this video, which I'll link in the description, he describes what he did was basically to try and find every scale, let's say of a given number of notes, like 7, and then discard all of the ones which have more than a certain number of semitones or tones, however you want to think of it, in a row. So for example, A sharp, B natural and C of 4, we could call those 4 tones in a row. So he's discarding them to try and make the total number of scales more manageable and just focus on the ones that have a unique harmonic sensation. This sounds like something that's lends itself to being solved algorithmically. You can, if you've worked with that kind of thing before, you can imagine this as a kind of thing where the algorithm would be quite elegant. You could think of this as just basically a general logical problem, but it is more interesting to me that it relates to sound, since each scale kind of has its own harmonic sensation that it brings when you hear it. This problem, I was doing some research looking into it, and I found this really great website if you're interested in this kind of thing. It's by Ian Ring, and I'll link this in the description. He's carried out a massive, or carrying out, ongoing, I guess I should say, study into scales, really. But this particular page on the website seems like a very good place to start if you're interested in just finding out some things about the general definitions of scales if you're not sure on them, but particularly in a way of representing them in which it would be straightforward for a computer to understand it. So I don't want to rehash everything he's already done in this video. I'm not going to talk about that. If you're interested in that, just go and have a read of this page. I found this whilst I was writing my version. So there's some similarities, some differences. A couple of the ones are that my root tone, I use the same kind of representation, except my root tone is on the far left and mine goes left to right rather than right to left. And also, I think as a constraint, he's using largest leap, whereas I'm using what I'm calling consecutive tones, which are just notes that are a semitone apart. Since that was Holdsworth's original approach as well. Really, they're exactly the same, because if you're looking for largest leap, what you're looking for there is consecutive zeros, and if you're looking for consecutive tones, or whatever you want to call that, you're just looking for the ones that are next to each other. So it's exactly the same, you've just swapped zeros for ones, but apart from that, it's exactly the same. So I'll share my implementation now, just kind of what it looks like. It's just one file of C, very minimal. Just a proof of concept, really. I can't imagine this would be useful for anyone, except if you're just interested in the actual algorithm side of it. Do let me know if you have any questions. I'm not going to harp on about it too much, just to keep it brief. But just a couple of demos what you might be able to do with it. Let's say we want every 7-note scale with no more than 2 consecutive tones. That's what these 2 arguments represent, the number of active pitches in the scale. So a major scale has 7 active pitches, with the 8th being the same as the first but 1 octave above. Hence octave 8 octopus, and so on. And 2, let's start with 2 because that's quite manageable. What we have here is these are 6 unique scales. They're not modes of each other, because this enumeration filters out modes, which means, let's say if you found Lydian, I'm going to assume that you've read that page and you've heard of the modes. If you found Lydian in the enumeration just through the brute force method, that is going to essentially tick off also Phrygian, Mixolydian, Aeolian, Ionia, etc. Because they're the same thing, just rotated. So these are, the output of this counts only unique scales. You're not going to get, because otherwise you'd get 7 basically per scale, per 7-note scale, right? Just to show a couple of, you could raise that constraint and then obviously you're going to get more. If you want to bypass the constraint, I'd suggest just putting in a random large number. Just obviously it's never going to be reached in a 12-tone system. So you can see the 66 unique scales, not counting their modes, just unique scales. You can see obviously there's going to be only 1 chromatic scale. If we want to say what else was 6-note scales, we can see there's actually more 6-note scales that are unique with no more than 2 consecutive tones than there are for 7. So really this is just a proof of concept kind of investigation into having this solved algorithmically. Like I say, if you have any questions or if you're interested about the algorithm and stuff, let me know. But otherwise, have a look on the GitHub, which I'll link in the description, if you're interested in this kind of thing. And yeah, thank you for watching.